Good morning to all of you, and welcome to this second day of the third EURECA-PRO conference on responsible consumption and production. Our day begins with a keynote speech by Professor Emeritus Markos Papageorgiou. And before giving the floor, Professor Papageorgiou, let's say a few words about his biography and his research. So Markos Papageorgiou received the Diploma Engineer and Doctor Engineer degrees with honors, both in electrical engineering from the Technical University of Munich in Germany in 1976 and 1981, respectively. He was a free associate with Dors Consult in Munich and with the Institute of National de Recherche sur le Transport et la Sécurité. My French are not so good in France. And later, he became a tenured professor of automation at the Technical University of Munich. Since 1994, he has been a professor at the Technical University of Crete, here in Chania, and 2 years ago, 2021, he retired and he has been a professor emeritus since then. He has also several other professorship appointments, one with Ningbo University in China, another with Politecnico di Milano in Italy, with École Nationale de Pont and Chasseurs in Paris, at MIT in Boston, the University of Rome, La Sapienza in Italy, and he has been also a distinguished visitor professor at Tsinghua University in China and a visiting scholar at the University of California, Berkeley, and of course at other universities. Professor Papageorgiou is the author or editor of 7 books and of over 500 technical papers. His research interests include automatic control and optimization theory and applications to traffic and transportation systems, water systems, and other areas. He was the editor-in-chief of Transportation Research, Part C. He also served as an associate editor of IEEE Control System Society Conference Editorial Board, of IEEE Transactions on Intelligent Transportation Systems, and other journals. He's a life fellow of IEEE and a fellow of IFAC. He received the DAD scholarship in 1983, in 1971, and in 1983 he received the Eugene Hartmann Award from the Union of German Engineers, and finally a Fulbright Lecturing Research Award in 1997. He was a recipient of the IEEE Intelligent Transportation System Society Outstanding Research Award in 2007, and also the recipient of the Outstanding Application Award in 2018. He is also the recipient of the IEEE Control System Society Transition to Practice Award in 2010, and also the recipient of the 2020 IEEE Transportation Technologies Award. He was presented with the title of Honorary Visitor Professor by the University of Belgrade in Serbia in 2010, and he received the title of Technical University of Munich Ambassador by the Technical University of Munich in 2021. He has been heading the Dynamic Systems Simulation Laboratory here at the Technical University of Crete since 1994. And he has received also the IEEE Intelligent Transportation System Society Institutional Lead Award in 2011. Last but not least, he was awarded 2 ERC Advanced Investigator grants, the first in 2013, I think by the acronym TRAMAN, and the second in 2019, known under the acronym Traffic Fluid. With no more words, please join me in welcoming Professor Papageorgiou. Professor Papageorgiou, the floor is yours. We're waiting to hear about road traffic control, past, present, and future. Thank you.
Thank you very much, Michalis. It is a great pleasure and honor to address the audience of this highly interesting conference. with the title just announced by Professor Lagoudakis. As we all know, transportation exists since human society exists, but of course in recent decades, the last century has been increasing steadily in importance, and of course it is a sector that consumes energy. I'm not an expert in sustainability, but I picked those numbers about the corresponding emissions, which are 23% of the total greenhouse gas emissions related to energy, but it is the sector that is increasing most rapidly, and there are predictions that these emissions will double by 2050. Of course, I'm talking about transportation in general, but road traffic is the biggest part of those emissions. And that's the subject of our presentation. Another thing we all know is that the motorized vehicle has been a very influential invention of mankind, has shaped even the image of our planet. If somebody would come from Mars and look at the Earth, one of the first things that would probably be realized are the highways, the roads, and all those vehicles moving on them. Of course, vehicles share a common infrastructure among them, but also with other users. And so it is necessary to have some rules. And this is the start of traffic management, traffic control. Have some rules that guarantee that antagonistic streams of vehicles and other users are crossing in a safe way. So safety is the first concern for traffic management, but in the last decades, as the density of vehicles, the number of vehicles, the demands on the roads increases more and more, we need to also look at efficiency of the traffic flow, and then traffic management becomes dynamic or real-time, as we would see, and this is the era, characterizes the era of today. Dynamic traffic management, which beyond safety also, of course, needs to address as far as possible efficiency. Another thing we all know is that human technology has made huge advances, particularly think about mobile telephony, internet, things that were unimaginable until 20 or 30 years ago. But there is one sector that lags behind, and this is exactly road traffic, and this is witnessed by the huge congestion that we have daily during peak periods all around the globe. And it is a sort of shame for the human civilization if you consider that even very simple creatures like ants seem to manage their own transportation problems more efficiently. I provide here this article. If you start reading the title, you think first it's an article about traffic control, but then the last two words reveal that it's not about human transportation, it's about ants, because ants, they form highways between a food source and their nest in two ways, and those two distinguished zoologists studied in depth the behavior of the ants on these highways. And in this article they document that the ants behave, of course taught by evolution, biological evolution, behave in the best possible way to maximize the throughput of their highway. Something that for us is still, of course, not the case, whether in urban areas or in highway areas. Traffic is depends on the match of two things. On one hand, the demand, which is the amount of vehicles, of drivers, of persons wishing to use the traffic network, and on the other hand, the supply of the traffic network, essentially the capacity of the traffic network. And these two things form traffic, which may be congested if the demand is higher than the supply. And so by this simple relationship, we can deduce easily what should be done if we want to mitigate congestion. Either we need to reduce the demand, or we need to increase the supply. And here you see various ways of reducing the demand, or attempting to reduce the demand, like modal shift, meaning that in many different ways you try to have passengers moving from their cars to public transportation, or avoid the trips via teleworking, online shopping, etc., things that are meanwhile very familiar to us after COVID-19. Demand management. A major measure in demand management is that you ask the users to pay for using the roads, something that is practiced in many places around the globe, or of course just harsh restrictions of vehicles where they can actually drive. On the other side, we may increase supply, increase capacity. How? The traditional way, which is of course not very popular meanwhile, at least in developing countries, is by expanding the road infrastructure. This is not deemed now to be the proper way if a basic infrastructure is already there. Providing information and guidance in real time to the drivers so that they may use parts of the network that are less congested, so exploit better the infrastructure, or traffic control. And as a matter of fact, and as I mentioned, our roads are indeed congested during peak periods, both in the cities and around the cities. And this congestion, without counting for the accidents and anything else, costs at least Europe 1% of the gross domestic product. Right? And this is rather an underestimate because it is from a few years ago. Another useful slide to gain a bit more insight into what happens is this one, in which we have a traffic network of any kind. It can be transportation, and it can even be other kinds of networks, which receives a demand at its origins by vehicles that would like to go through this network to reach a destination and for the exit flows. So, assuming that the demand is not changing, if we want to apply control actions to the network to minimize, obviously, the total time spent by all vehicles in the network, then it is very easy to understand and also easy to prove mathematically that this is equivalent to maximizing the exit flows. Because if the entries are given to spend less time in the network, you need to maximize the exit flows. And as a matter of fact, congestion reduces the exit flow, blocks the exits of the network. And this is a reason for a generalized congestion that we witness today, as we will also see in a minute. To better understand this, let's compare other kinds of networks or queuing systems. If we have a simple queuing system, like you go to the airport to check in, and if the demand, the number of passengers, of clients, is higher than the number of employees, the number of counters, there will be a queue. So you will experience a delay. However, the characteristic of a simple queuing system is that the capacity of the system, the serving capacity of the system, is constant, roughly. It's not a function of the presence of a queue or of the size of the queue. The employees will work at the same or similar pace whether there is a queue or there is no queue. That's a simple queuing system. There are other systems like water systems where higher demand and congestion, higher water level, means higher pressure and higher outflow and lower travel times. So in water systems, if you flood it, you get more out of it due to the pressure. It's not like a simple queuing system. What about traffic systems? Well, in traffic networks, for reasons that we will not discuss in detail here, any congestion leads to a degradation, a reduction of the capacity of the system, and a reduction of the exit flows. So what happens is that if you have, in some link in the network, you have the local demand being higher than the local capacity, then you will have a queuing, you will have a congestion. And this congestion will degrade the local capacity, and this will, of course, accelerate the increase of congestion, and this will lead to further increase and further of congestion and further degradation, and so on, so that eventually we get a vicious circle of events, and at the end we have a network that is underperforming, strongly underperforming due to the degradation. In fact, during generalized congestion in the network, if you measure the demand that is being served, it is much less than the nominal capacity for which the network was constructed. The system is underperforming. What I'm trying to say with this is that the generalized traffic congestion that we witness in urban areas or in highway networks is not only due to high demand. It is also because of the degradation and this vicious circle caused by the congestion. And this is a very ironic fact. We construct a very expensive infrastructure, particularly as far as highways are concerned. And this infrastructure capacity, nominal capacity, is not there at the only time we need it, which is the peak period. So, at the off-peak period, we don't need it because the demand is lower. At the peak period when we need it, it is also not there because the congestion has degraded. And so, one way to mitigate this situation, among others that I mentioned earlier, is by traffic control, by considering the network as, the traffic network, as a controllable system, and trying to operate it as best as possible. And this brings us to automatic control, which is my original discipline. Automatic control is the discipline that develops and applies methods, anything that has to do with automation in many different domains. And what you see here is the basic scheme of any automatic control system. In this case, we would like to control a process. Let's say, for understanding, the process would be the temperature in this room. We'd like to control the temperature in this room, right? Now, this process is influenced by a number of quantities that are not in our hands to influence. And therefore, we call them disturbances. In the case of the temperature example, disturbance, the most important disturbance is the outside temperature. You cannot influence the outside temperature. Or the number of persons in the room, or the number of electrical devices that produce heat, and so on. All these things are disturbances that influence the process, but are not in our hand to influence. In order to take influence on the process, we need actuators, we need special devices, like heating devices, air conditioning devices, which are in our hand to operate and do influence the process. So there is an automatic control loop always, there is a feedback loop. We install sensors based on which we know or try to have a picture as good as possible about the state of what we want to control, the state of the process. And these measurements, these real-time measurements, are fed to a computer. You see here the separation between the physical world and the computer world. So they are fed to a computer, they are processed, and then they reach the brain of the control system, which is the control strategy. Why is it the brain? Because it makes decisions in real time. This loop is run all the time. Measurement action, measurement decision action. So the control strategy tries to influence the process in a way that corresponds to our specific goals. For example, in this example of the temperature, we set a desired temperature at the device, and then we expect the system automatically to reach that temperature. Right? So this is an automatic control system. And if we are talking about road traffic control, the elements of this system are the ones listed here in conventional traffic management. So the process is, of course, the vehicle flow. The sensors, there are various technologies of sensors installed in different links within the network. They are spot sensors in the sense they measure just at one location. Communications between the elements of the control loop are wired, typically. Computing is hierarchical. Usually you have some controller, some computer locally, but then all these local computers are connected to a central control room. And, very important, actuators are roadside. They are on the side of the road, which implies that everybody gets the same command, the same message from the system. Every driver gets the same message. And you see here some examples of such systems. For example, here, it is a variable message sign system that informs and guides drivers. This is from the expressway network in Scotland. This is a variable speed limit system. You see the speed limits which change in real time according to the traffic conditions. This is from motorway M25, the ring road of London. This is a RAM metering system from Melbourne, Australia. What it does is you have here the freeway, and this is an on-ramp, and you see the traffic lights with which you can control how much traffic will enter the highway in the aim of maximizing the throughput and avoiding congestion on the highway. And this is just an urban road map where, as you know, there are traffic lights at every important intersection which need also to be operated. So all these systems that are around, they need, they have roadside actuators, the same for all vehicles, for all drivers. And in fact, our lab has worked in all of these areas, and we have many operational tools in 5 continents of these systems. And I would like just to demonstrate to you via simulation a variable speed limit system. What we see here is a highway. There is a lane drop at the end, for example, because of a work zone or other reasons. And this forms a bottleneck. So if the demand is higher than the capacity of the bottleneck, then you will have congestion. So in the lower video, there is no control. In the upper video, you have a variable speed limit here, about 500 meters from the upstream of the bottleneck, which you will see in real time being changed, because in the upper system we have a traffic control system measuring at the bottleneck, and depending on the density that it measures there, it reacts, and the variable speed limit tries to hold back traffic so that you never allow congestion to form. I was expecting to see the video. Maybe I should operate it from the... So actually there are two videos, one for the control case and one for the no control case. This is the start of the simulation in which the demand arriving is still lower than the bottleneck, and so nothing of importance happens. So let's go further in the simulation. So you see already here that in the case without control, we have already a queue that has formed because that was already very far in the simulation, no problem. So what happens here is that whenever you have a higher density measured, this variable speed limit will reduce the speed limit to hold back traffic and dissolve any possible congestion that forms here. So this is an example of going slower to arrive faster. While here, as you see, a queue has formed, and due to the queue, the outflow is about 15–20% lower than the maximum possible outflow, and so this leads to a corresponding improvement. So that was about the recent past and a big part of the present. That's the state of today. So let's move a little bit to a more recent present and the short-term future. What we have today is a number of vehicle automation and communication systems that are being developed, and that can be classified into two axes. The first axis is about vehicle automation. Vehicles become more and more automated, or intelligent if you prefer. There are already many systems that are available in the market. Most of the new vehicles dispose of an ACC system, adaptive cruise control. What is it? It is the ability of the vehicle to follow at a safe distance a slower vehicle in front without you needing to touch the brake or the gas pedal, right? Or also pilot assist systems that keep the vehicle in the middle of the lane without you touching the wheel. These systems are already in many models. But of course, the evolution goes farther to driverless driving. This is the, let's say, the last goal. There are already vehicles, as we may know, that drive without driver, you know, pilot vehicles, but also ordinary vehicles, like in San Francisco in the last months. You can take a taxi without a driver on the streets of San Francisco, and more will follow. So that's about vehicle automation. Connectivity means that vehicles have wireless channels to talk, communicate with other vehicles around them, and also with the infrastructure. So these changes, they bring along, these are changes in the vehicle itself, but they bring along also pretty important changes to the traffic management loop and its elements. For example, the process, of course, is still the vehicle flow, but now vehicles have different behavior than conventionally. Sensors. Since vehicles are connected, they can send information to the control center about their speed, about their distance to the front car, and so on. So you don't need sensors, because vehicles become sensors that send much more information and much more precise information about the current situation. Communications. Not only are they wireless, but the most important thing, as I mentioned, is that you have a lot of new channels between vehicles and infrastructure that can be exploited for better safety and better efficiency. Computing. What we have essentially with intelligent vehicles is a big number of moving, interconnected computers. So those computers can undertake tasks that conventionally were reserved to the traffic control center. And last not least, actuators. If vehicles are connected, they can receive all the messages on board. So you don't need to have roadside signals or messages that are the same for everybody. You can have individualized signals and messages and information. And we can see some examples. All these things, of course, have implications for the traffic flow. Not always for the better, unless they are exploited in a proper way. And so the first ERC advanced grant that we got, that the chairman mentioned, was about looking at these things for now and short-term future in an environment where we have mixed traffic, meaning both automatic vehicles at different levels of automation and connectivity, and human-driven vehicles. How can we exploit the increasingly available capabilities of vehicles to make traffic safer and more efficient? So that was the content of the Traman 21 project, and I can give you some few highlights of it. If it decides to switch. do it. Yeah, this is an automatic vehicle. Oops. So this is an automatic vehicle among manually driven vehicles, and you can have any percentage of automatic vehicles. The question is, how should it behave in a population of automatic vehicles? You see it here, driven by an algorithm, driving. It has three basic goals. The first and most important is no collision, safety. The second is that the driving is comfortable for the passengers. And the third is that it tries to reach a desired speed, if possible. And you see it trying to change lanes and make everything possible to satisfy those three goals. This is the second example that you probably, most of you know, the famous GPS. What is it? Well, GPS is an individualized message for you, as I mentioned earlier, because you enter your destination and it guides you to your destination. So nothing to do with roadside messages. And of course, you may not be aware, but you are also connected to the corresponding center of Google, of TomTom, whatever system you are working on. So that's how they know what is the current state of traffic, because they get messages every few seconds also from you, and not just from you, but from many other cars, so they can anytime be aware about what is the situation to be able to guide you in an appropriate way. Another potential application is that due to the individualized commands, you can better balance traffic on highways, for example. Usually, the drivers by themselves, they are not able to optimize the traffic flow, to optimize their assignment of lanes, to optimize the traffic flow, to retard or avoid breakdown in congestion. And it wouldn't be possible with a roadside system, because what should you tell? Every 10th vehicle change lanes to balance better? That's not possible. But if you can send individualized commands, then you can balance traffic on the different lanes better, and in this way avoid congestion. Another example, the GLOSA systems, green light optimal speed advice. What is it? Well, every driver among you probably has had this dilemma. You are approaching a signal, a traffic signal, which may be red or green. At the time you see it from, let's say, 200 meters distance, and you don't know how to behave in the aim of crossing without stopping. Should you accelerate? Should you decelerate? Should you go by the same speed? You don't know. So GLOSA are systems that help you address this dilemma and cross, if possible, without stopping. At green, of course, but without stopping. So there are many apps of this kind, even for iPhones, where you get either this message when there is no realistic possibility to not stop, or it guides you regarding your speeds, either maintain your current speed or increase or reduce your current speeds to be able to cross at green. And such systems may reduce fuel consumption and, of course, emissions by as much as 20% when applied. And let me now take a little bit more futuristic view of traffic. This is the second ERC grant I was talking about under the name Traffic Fluid, which is about traffic not tomorrow, but at a time where most vehicles are automated and connected at high levels. And so we call them CAV, connected automatic vehicles. And traffic fluid is proposing two principles for the traffic of the future, maybe not the nearest one, but of the future. The two principles are that there should be no lanes, no traffic lanes, the first one. And the second one is that vehicles behind can influence the driving of vehicles in front, which we call nudging. So to better understand why these principles, let's think about human driving. Humans, we have a perception limitation, which is that we can only look in one direction at a time. We cannot look all around simultaneously. And when we are driving, of course, this direction should be the forward direction, because that's where we are. This has some consequences. For example, in the 1950s, traffic lanes were introduced. Before that, there were no parallel traffic lanes. You could drive anywhere, even on a highway. There were no lanes. Why were traffic lanes introduced? To simplify driving, human driving. Because in that case, driving reduces to car following. You just look at the other vehicle in front of you and try to keep a safe distance. Of course, it has also consequences. First consequence, fixed lanes must be wider than the widest possible vehicles, so you waste a lot of space laterally. And second, you need sometimes to change lanes, and this is a very risky maneuver. 10% of all accidents, road accidents, are due to lane change. A second consequence of the same thing is that when you drive, you just look ahead, you don't look behind. So there is no influence of traffic behind you on your behavior. And when you make the step from microscopic to macroscopic, this has a consequence. The flow is anisotropic. For example, there is no pressure, like we mentioned earlier. Water has particles, push the particles in front. In traffic, they don't. And this has consequences for the traffic flow. You can make it, you can increase capacity, you can increase stability if you have vehicles being influenced in their driving by vehicles behind. What about CAV? Well, CAV is quite a different thing than human driving, because they can look all around simultaneously, reliably, fast. They can extend the area of their perception by communicating with other vehicles. And of course, they make very fast and computer-based decisions, algorithmic decisions. So they are quite a different thing. And in fact, it's not only in gas and water and other fluids that we see lane-free movement. Even in nature, in living nature, we see lane-free flows, like the bird flock that you see here, or the fish school that you see here. They go driverless, and there is no central control, there is no coordinator, just decentralized action by every individual. And of course, it is 100% safe. I mean, we have never witnessed birds falling down because they crashed with other birds. Right? And even in human society, if you look at pedestrian flows or cyclist flows, you see that they form no lanes. In fact, in this video that we will see from Beijing Tsinghua University, which is a bicycle avenue, you see that there are two directions, and the boundary between the two directions is not marked, but is virtual and is moving spontaneously depending on the corresponding demand. Can you switch, please, the video? It's below the, yeah. So you see here the demand outwards is much lower than inwards, so the separation of the two is moving to the right. Next slide, please. So, our working assumption in this project is that CAV do not need lanes and do not need anisotropy. These seem to be four signs from human driving here. And we investigate smooth two-dimensional driving, smooth in the sense that you don't have abrupt lane changing, like in conventional traffic, or automated traffic with lanes. Higher lateral occupancy, and that means higher capacity. And what is very important, we will see it also in a minute, in a lane-free road, if you widen the road by 10, 20 centimeters, 1 meter, you increase the capacity, because vehicles spread and cover that part of the road and reduce density and increase speed. While, of course, in lane-based traffic, you need at least one additional lane over several kilometers to increase capacity. And we will see that this can be exploited in some ways. So we know for any fluid that the emerging flow behavior is an outcome of what the particles are doing. And in that sense, if we have the liberty to be without lanes, to be non-anisotropic, the research question is, what should be the movement strategy of individual vehicles so that the emerging traffic flow becomes optimal or well-behaved? And in that sense, we may talk about a future traffic flow that corresponds to an artificial fluid, meaning an engineered fluid. Because by specifying in appropriate ways the movements of the vehicles, we can influence in a beneficial way the properties of the macroscopic traffic flow. And I will give you some few highlights of some things that are related to this traffic fluid thing. Could you please start the video if possible? So what you see here is a lane-free ring road. The camera follows this vehicle, and every vehicle drives by deciding about the next 8 seconds, and whenever it makes a decision, it broadcasts this decision to other vehicles so that they know what very likely it's going to do, but they never apply those 8 seconds. Usually after every second they replan. The vehicles have different desired speeds, so you may see some being slower, some being faster, either because the density increases or because they have a different desired speed. So you see the width of the lane, if you would have lanes, would suffice for barely 3 lanes. But you see that vehicles may drive also with 4 vehicles laterally. So let's keep this. Now, the same concept here is also applied, but for a group of vehicles simultaneously. So we optimize with a single optimization problem the behavior of multiple vehicles, of a group of vehicles. This is an artificial scenario that I will present here, and I will tell you why we do that. So you see here 7 vehicles. You see here 7 vehicles driving. The first one has the lowest desired speed, and the last one has the highest desired speed. So the last vehicles need to overtake all the previous ones. And on the top of that, even avoid some red obstacles while driving lane-free on the road. Driven by a single optimization problem. Why do we do that? This is just the first step to test the tools. The next steps is to try to see how vehicles could drive in groups like the birds, forming flocks, deformable flocks with the same speed. Or they could drive in a platoon, one-dimensional platoon, which can move like a snake in traffic, so that you have smaller distances among vehicles of the group, but higher distances for safety among different groups. Okay, this is another control strategy. This is a reactive control strategy. Again, for lane-free, here you have also exits, and these cars will merge again. Everything based on decentralized control strategy for every vehicle that, as you see, swiftly, drive every vehicle on the road. You may recognize this monument, the Arc de Triomphe in Paris, and this is a photograph of the roundabout. This is the Arc de Triomphe. This is the famous Avenue des Champs-Élysées. This is a very complex traffic infrastructure. The width of the roundabout is 38 meters, like 12 lanes, urban lanes, right? And you have 12 radial streets, bidirectional. So that means you have 12 times 12, 144 different origin-destination movements on a roundabout of 38 meters. You may imagine this is a very complex thing, and there are no lanes anyhow. If you drive on these infrastructure, there are no lanes. It would make sense to have lanes. And in a keynote in 2021, Luc Juliard, who is an icon in artificial intelligence and autonomous driving, he said, in his opinion, the fully driverless vehicles may never exist, and he mentioned two reasons, and one of the reasons was that they would never be able to drive on this roundabout. So that was for us, we were working lane-free anyhow, so it was a trigger to try to demonstrate the opposite. So, can you start it? Okay. Yeah. So we developed a movement strategy for vehicles that allows to move even at high densities on this roundabout without collisions, of course, and guaranteeing that no vehicle with miss its exit. So the color of the vehicles here, every color corresponds to one exit. So we managed to address this issue. Let me go to the next highlight, which is internal boundary control, a very strong point for lane-free traffic. What is it about? Consider a road or a highway with a total width W. Total means for both traffic directions, direction A, direction B. Of course, conventionally, you would have usually an internal boundary, which is a straight line in the middle. But if we have lane-free traffic, we may consider the internal boundary to be a function of space and to be changing in real time, driven by a control strategy, depending on the traffic conditions. So if you have a lot of demand on this side, then you shift it upwards or vice versa. And to just demonstrate without going into design details, we see here a highway subdivided into sections, In the upper case, we have no control. In the lower case, we have internal boundary control. And we use as a demand on the upstream side, first a peak in direction A over time. This is time, and this is the demand. And then a peak in direction B. And can you start the video again? So now you see, because of strong traffic flow arriving from here, the system moves the boundary upwards, while in the no control case, you have a congestion forming at the merge of the on-ramp with the traffic flow. Right? Here the congestion is completely avoided by the internal, thanks to the internal boundary control. And then when flow becomes stronger in the other direction, the automatic control system moves the boundaries of every section here downwards to avoid the congestion that would form or will form in the no control case, again in the merging section over here. And this is, of course, a simulation with macroscopic models, but we can also test it with a microscopic simulation. Can we go to the next video and start it? Yes. So you see here the same thing with microscopic simulation. You see the internal boundary, actually two internal boundaries, the green for the lower side and the red for the upper side. You see that it is not in the middle, it is already shifted because the density in direction A is higher than in direction B, and this boundary is being shifted every minute depending on the traffic conditions to facilitate traffic, to mitigate, to avoid congestion. And a last highlight, lane-free, signal-free intersection, crossing. Of course, usually in such intersections you have traffic lights, but again, we can optimize all vehicles around the intersection simultaneously so that they can cross simultaneously without collisions, of course, and as efficient as possible. Let's see if I can start it from here. No, can you please start? So you see how the intersection of the future may operate with automatic vehicles getting instructions from a control center. That was the last highlight, and thank you very much for your attention.
Thank you very much, Professor Papageorgiou. This was a very interesting topic, and we may see all these proposals implemented in the future. So we have time for one or two quick questions because we're running a little bit late in the schedule, and afterwards there is coffee break. Okay?
Markos Papageorgiou, Chania University of Technology. Thank you for a great presentation. It's really enlightening presentation because it's line-free. Street is something very interesting, and I think it's kind of, I don't know, out of the box thinking. Because when you think about computers driving vehicles, you always think about rules, lines, and so on. But I have a question about this signal-free crossing. In computer science, because I'm from artificial intelligence, in computer science we have such a problem as process starvation. It can happen that one of the vehicles, automatic-driven vehicles, just waits for our vehicles infinitely, because it just waits, it just has bad luck. How do you handle this problem?
Yes, this is a good question. We may face it in a second step of our research, when we will try to make vehicles cross maybe less efficiently, but in a decentralized way, each one making its own decisions. But in this example that I mentioned, and also other groups are working in this area, we usually consider the problem as a joint optimization problem for all vehicles. So since we have a joint optimization problem, we have implicitly a cooperation between vehicles. The optimization problem, unless it is stuck in a very bad local minimum, it will not allow any vehicle to stay forever just to let other vehicles cross. They all must cross, and they all must cross in a reasonable time. I agree that something like what you described might happen in case you have decentralized strategies without explicit cooperation among vehicles. Then some things like that might happen, and we will need to address it.
By the way, one addition, a crossing like this reminds me Indian crossing in India, and it works somehow for humans as well.
I must confess, after the first ERC grant, which was a lot of work, I did not intend to go for a second one, but when I went to give a short course in New Delhi, I got the idea about the traffic fluid concept, lane-free traffic, and nudging of vehicles, influencing vehicles from behind.
Thank you very much, Professor, for a very interesting presentation. My name is Anna Mapaszak, I represent Warsaw School of Economics. And I have a couple of questions related, first of all, to one of your first slides regarding the greenhouse emissions coming from transportation. So my first question would relate to the issue of applying some of those interesting solutions to the public transportation. I understand that this is one of the matters related to the cost efficiency of some of these solutions. Many of the countries are introducing interesting ideas about encouraging public transportation as a solution to the traffic and greenhouse emissions and climate transformation. So I would have a question to that. And my other question is related to your, I would very much value your opinion about is there a future for electromobility and the hydrogen-powered electromobility and the hydrogen-powered transportation. Thank you very much.
Okay, so first question, very good question. What about public transport? There are different ways. I mean, public transport, as we know it today, is not something. This is something that will also gain with appropriate measures from these developments. But what is new, or relatively new, and might be really widespread in the future, is demand-responsive transport. That means not really public transport, but vehicles, possibly even automatic vehicles, that decide automatically based on calls by potential passengers to go and pick multiple passengers and bring them to their destinations by themselves. So there is a lot of research, we are not involved in that, by many different disciplines, including social scientists about the consequences, that are working on developing operational systems for demand-responsive sort of public transport, as I mentioned, on-demand transport. And this is probably going to be something very substantial that goes in the direction of public transport, but is not really exactly public transport as we know it today. Regarding the second question, again, I'm not an expert in electric vehicles or hybrid vehicles, but I may be closer than others to these questions, although not active in that research. I believe that, you know, the last technical issues that we have with electric vehicles are being resolved. The electric vehicle fleet is increasing steadily, and most probably in a couple of 2 or 3 decades, nobody can exactly predict, the whole population of vehicles, or almost all vehicles, will be probably electric, possibly to some extent hybrid. And this is a good evolution, I believe, in many different aspects.
Now there are many questions, but unfortunately we won't have time for one.
Yeah, thank you very much for this interesting topic. I believe that without lanes and without signals, you can really organize any process if it's automated. As you told, you have sensors and then you can check it. And I think about the airport, when the luggage is distributed to different airplanes, there's nobody ruling something, everything is by sensors and automated, let's say, decision making. But now we have, point of view, 2 aspects. One aspect is that humans use a car because to have fun. Huh? And you mentioned, yeah, there is someone who wants to ride fast, and somebody wants to ride slowly and look at the landscape or orientate what is the next. And yeah, so so this human factor is one. This means you exclude this effect why people are using the cars. And the second one is the legislation. When cars crash at sea and a bird fall down from the heaven, what is then happen? And this means all the traffic rules completely ignored. There is no left for right or right for left, and there is no signal green or red or something. So the cars go automatically, and there are people sitting inside, and then something is wrong, because we believe that GPS is working all the time, and computers are working all the time. There is no any misunderstanding, and how these aspects are, let's say, considered in the research about the realization of such a system. Because the transition period, I think, is very difficult. If you have some cars, they are ruled automatically, and then others with people behind, then I think it becomes very, very difficult from a heuristical point of view.
Yes, thank you for the questions. First question, you said some humans have, you know, fun with driving and so on. Yes, but you know, that's life. There is always a change. There is an evolution. There are some very nice photographs, if you look in the internet, from New York 5th Avenue. I'm not sure the year is the correct, but let's say 1912, the year 1912. 5th Avenue congested by carriages with horses, and somewhere one single car. And then 5 years later, the same area, congested, everything is cars, and just one carriage horse. Well, people who liked the horses, they may have to go to do it as a sport, and life goes on in a different way, possibly. And of course, these brought about significant changes also in different professions, whole professions, thousands of people who just stopped their business because there was no client. People who were taking care of the horses, of the carriages, of everything, while new businesses opened for the cars. Second question, that's a very reasonable question indeed. There is the Convention of Vienna that states that in case of accident, of course, the drivers are responsible, and in principle they do not allow anything else to happen because they need responsibility. However, the car manufacturers and the government are already working in this direction to change the legislation. It is an open question if there is a collision, who is responsible? The driver, if there is still a driver, the car manufacturer, or, I mean, so it is a valid question, but we are not, lawyers, so there are corresponding, legal issues, persons discussing these issues and changing it. As I mentioned, already we have in several states in the United States autonomous vehicles driving by themselves, of course without breaking the law. There are, by the way, even other issues that are very important, like cybersecurity. What if somebody can intrude the car and caused by an incident just by intention? And several other issues that appear, and they are treated, hopefully in a successful way.
Well, let's thank Professor Papageorgiou once again. Thank you very much.